integration. Okay. Okay, again, good morning, everybody. So today we'll continue our discussion of partial fraction decomposition. So we said last time we use partial fraction decomposition when we are dealt with a function which is a polynomial over another polynomial. The first requirement is to make sure that the degree of the denominator is strictly larger than the degree of the numerator, because otherwise you'll need to do long division. And the goal here is to try to write that original fraction p over q in terms of the sum of smaller functions or smaller fractions. When I say smaller fractions, the denominators should be of lesser degree than the original denominator q. And the decomposition will depend on what are the factors of q. So the next step after checking the degrees, if we have the right form, is to factor the denominator, which reminds us that you need to go back to those basic techniques in algebra or pre-calculus like factoring, and then later we'll see how to solve systems of linear equations. Those are very important things that you need to remember. Even long division also, which is reminiscent of the previous chapter where we needed some other techniques from previous classes or from previous sections. So math is very sequential, so make sure you remember all the prerequisites. Okay, then I guess last time we did a couple of examples, if I'm not mistaken. So we did problem 17, where when the denominator has unique linear factors. I guess that's straightforward. Problem 26, we considered a case wherein we have a repeated linear factor in the denominator. And I guess that's it. So for today, let's look at some additional examples. So these are different from the ones in the worksheet. So that means there would be more problems that will be left to you. So you can try answering the rest of the problems from the worksheet. If you have nothing to do over the spring break, try to practice with these. So I'll give you some examples, some new examples. So there are some cases wherein you'll not suspect at first glance that you're going to use partial fraction decomposition. So for instance, you're given the integral of secant squared x over tangent cubed x minus tangent squared x dx. So if you look at this, it is not a rational function because the top is not a polynomial, neither is the denominator. And then you might be thinking, oh, maybe I can do u substitution. The usual suspect for the u substitution is the entire denominator. But if you let u to be the entire denominator, then you'll have a complicated du, which is impossible to get from the top. Okay. And then you realize that, oh, I'm working with trig functions. Maybe powers of trig functions will help me. But if you go back to our notes on powers of trig functions, that only involve the product of two powers. But here we have a binomial term, which is not exactly a power of a single trig function. So that's out of the question. So that means if I look at the denominator further, it looks like it's some sort of a polynomial, but a polynomial in tangent x. So maybe a u substitution perhaps as a starting step will reveal that, oh, this is polynomial in form. Okay, and true enough, I can let u to be equal to tangent x. What's the clue that I will let u be equal to tangent x? So you will see that the numerator has a secant squared, and the denominator is purely in terms of tangent. And remember, the derivative of tangent is secant squared. So basically, oh, there might be a reason why I have a secant squared on top. And true enough, if you let u equals tangent x, then you can use that secant squared in having the appropriate du. Okay. Now, if you perform the substitution, you'll have du on top over u cubed minus u squared. okay? Or you can look at it as 1 over du, oh, sorry, 1 over u cubed minus u squared du. At this point, u substitution won't still work. There is no trigonometric substitution for u cubed minus u squared. And so what we'll do is try to do partial fraction decomposition. The denominator is degree 3. The numerator is degree 1. So it's perfect for partial fraction decomposition. So we proceed to step 2. We need to factor the denominator, right? So you factor the denominator this way, and we can decompose the fraction in terms of smaller fractions, right? Now, let's look at the first factor. The first factor is u squared. There are two ways on how to look at it. You can look at this as a quadratic factor u squared, and that's what I'm going to do. So I'll have a u squared here, and then u squared is quadratic, so its numerator will be a generic linear function, right? Remember, the numerator will always be 1 degree less than the original factor. The original factor is u squared, degree 2, so the numerator will be degree 1. Oh, but this should be in the variable u. Okay. Another way to look at it is you can look at u squared to be a repeated linear function, linear factor u. So, but you will get the same answer. So an alternative here is to write this as a over u plus b over u squared. But this guy, when simplified, will give us this. So either way, you'll get the same answer. Okay. Now we'll go to the second factor. The second factor is u minus 1. So u minus 1, non-repeated, so it gets 1 partial fraction. And the numerator would be 1 degree less than it. So let's put a d there. I'm just reserving the u for the arbitrary constant after we integrate. Okay. And then you have two options at this point. You can solve for the values of a, b, and d before doing the integration, but I usually prefer to do the integration first because if I am to decide how to distribute the partial credits for partial fraction decomposition, I would like to give more partial credits if you have done the calculus parts, which is basically performing the integrals, performing the integrations, right? And in some cases, that's easy. For instance, here, I can write this as a, okay. I can split this up into two cases, right? So I'll have an a over u plus b over u squared. So what I did there is simply perform the division. Au over u squared is a over u. B over u squared is b over u squared. Plus d over u minus 1 du. And I'll just imagine a, b, and d to be constants. It's just that we don't know what their values are at this point. But I can integrate nonetheless. So the first one would be a ln of absolute value of u, right? Remember, a over u will have that integral. And then this would be plus b u to the minus 1 over negative 1, right? Because this is b u to the negative 2. This will be its integral, plus d ln of the absolute value of u minus 1, plus the arbitrary constant c. Or you can rewrite it as a ln of the absolute value of u minus b over u plus d ln of u minus 1 plus c. All right. So at this point, I'm done with all the calculus steps. So all that remains would be the algebraic steps, which is basically solving a, b, and d. All right. Now, maybe I can go back also to the original variable. Remember, the original variable is x, but u is tangent x. So I can write it as a ln of tangent of the absolute value of tangent x minus b over tangent x plus d ln of the absolute value of tangent x minus 1 plus c. All right. Now I'll solve for the values of a, b, and d. And for that, I need to use my partial fraction decomposition. Okay, copy. So here, this is 1 over u. So, okay. So remember what we are decomposing is 1 over u squared times u minus 1. Okay. Let me just put this here. Okay. So this guy means, okay, I'll do the cross multiplication. So I'll have 1 equals au plus b times u minus 1 plus du squared. And this should be true for all u's. All good? Since this is true for all u, then I can pick any value of u I want and plug that in. So for instance, I can choose u to be equal to 1. Why do I think that is convenient? Because if you plug in u equals 1, look at this guy, that will become 0. So this entire thing will be gone, right? So we'll be left with 1 equals d, which is basically 1 value down. Now, what do you think is the other good value for u? Again, you can choose any value if you want. But I guess what would be the most convenient choice? I can let u be equal to 0, right? Because if that's the case, then this guy will vanish, okay? Leaving us only with what? 1 equals u is 0, so b times negative 1. I'll have negative b. Or in other words, that gives us b equals minus 1, okay? And 2 down. We're just down to a single unknown constant, which is a. And for that, we ran out of good values for u already. So let's pick an arbitrary value. I'll stick to a small number, say negative 1, but it's up to you. You can choose your favorite number. But if u is equal to negative 1, left side is still 1. But the right side will be what? We'll have negative a plus b times negative 2 plus d. All right? So all I did there was to plug in u equals negative 1. And then, I already know what b and d are. So I'll use their values. So I'll replace b by negative 1. So this would be negative a minus 1 times negative 2. And d is 1. So I'll have that. Then I'll subtract 1 from either side. So I'll have 0 equals negative a minus 1 times negative 2. Divide both sides by minus 2. So I'll get 0 equals negative a minus 1. And that tells us finally that a is equal to negative 1. Okay? And with this known, then we can write our final answer. Remember, we started with the integral of secant squared x over tangent cube x minus tangent squared x dx. We already knew that the answer will be of this form. Okay, hold on. Let me put this in the bottom. All right. And then let's plug in the values of a, b, and d. So I already know that b is minus 1. Okay. And then b is what? B is also negative 1. So I'll have a negative 1 for here. And then d is 1. So I'll just delete that one there. Okay. Okay, and that's our final answer because here all integrals are gone. But you can rewrite the answer this way if you want to impress with your knowledge of prerequisite stuff. So you can write it as ln of absolute value of cotangent x plus cotangent x plus ln of the absolute value of tangent x minus 1 plus the arbitrary constant c. This solution looks better, but it's not required that you write your solution that way. This actually is perfectly fine with me. Okay. Any other questions? Any questions? Is everything clear? Or perhaps let's look at another example. Are you already on a spring break mode? That's why you are really quiet, though you have always been quiet. And now I don't know if that's because you understand everything or you don't understand anything at all. So shoot me up with an emoji, at least an emoji on the chat so that I know your reactions. Okay, while waiting for that, hopefully somebody will respond. Okay, so let's look at this example. Don't forget the first step. That's very crucial. Remember, we want to make sure that the degree of the denominator is strictly larger than the degree of the numerator. In this case, oh, spring break, right? But I don't expect to have a break next week. I should be busy with my dissertation. That's a side note. So let's look at this, okay? They have equal degree, so we need to do long division first, okay? So spring break should wait. Let's do long division first. So if you remember long division, the divisor goes here. The dividend goes inside this roof, okay? Then we divide. Hopefully you still remember how. X squared divided by x squared, that's going to be 1. Then multiply, we get x squared minus 1. And then subtract, we get 1. This is the quotient, and this is the remainder. So what happens is that you write the quotient, 1, that goes there, plus the remainder all over the divisor. Okay? So again, what happened there? If you forgot, the quotient goes there, and then the remainder will go here over the divisor. Okay. Now we don't have a problem with the first term. The first term is x. We can is 1. We can integrate it as x. So we'll be left with the integral of 1 over x squared minus 1 dx. There should have been a plus c here when I did the integration, but I'll just say that that constant is still inside the second integral, and I'll reserve putting the arbitrary constant up in the end of my solution, okay? Just to not make the solution look messy, right? Okay, now on the second term, we don't have any formula for this. U substitution won't work, so we need to do integration by parts. And note that the denominator can be factored as x plus 1 times x minus 1 dx. That's another important thing to recall, how to factor, at least the basic polynomials. Okay. And then how do we do the partial fraction decomposition? Luckily, both factors are linear and non-repeated. So in the decomposition, we'll have a over x plus 1 plus b over x minus 1 dx. And luckily here, it's just a constant over a linear function. If you have a constant over a linear function, I know you can now imagine what will happen. It will just be a natural log, right? So here we'll have x plus a natural log of absolute value of x plus 1 plus b natural log of the absolute value of x minus 1 plus c. Okay. Is it fine if I leave those details? Because for instance here, to get to this answer, okay, for this one, what you'll do is you let u to be equal to x plus 1, du is dx. So that integral will just be du over u ln of the absolute value of, oh, sorry, there's an a there, a ln of the absolute value of u. That's how we got this. Okay. So I hope that's clear. So I am not putting in all the details in the solution there, the use substitution, because I know whenever I have a linear function, it will always be a natural log. But you need to be a little bit careful, especially if the coefficient of x or the slope of that linear function in the denominator is not equal to 1. For instance, you might encounter something like this, a over, say, 1 minus 2x dx, okay? Now, you need to be careful because here, if you let u to be equal to the denominator, du will be equal to -2 dx. So du over -2 is equal to dx. So this guy would be the integral of a over u times du over -2. Okay? So that integral will be -1/2 a ln of the absolute value of 1 minus 2x. So there can be some extra constants that will pop up, right? Actually, the general formula there, it is the reciprocal of the slope. So here the slope is -2. Take the reciprocal of it, -1/2, that's a constant in front, okay? So, but luckily here the slopes are just 1. So that means the coefficient in front of the integral is just equal to 0. It's just equal to 1. Okay, is that good? I will not be including those details in this solution. I'll just keep in mind what will happen after I do the use substitution. Okay. Now we're done with all the calculus steps. So what remains to be done here is to solve for the values of a and b. Okay. Now remember what do we have here? We have 1 over x minus 1. X plus 1, x minus 1. We decompose it as a over x plus 1 plus b over x minus 1. We do the cross multiplication, so we get 1 equals a times x minus 1 plus b times x plus 1. And this must be true for all x's. That gives us the liberty to choose whatever x you want. The most convenient, maybe, is letting x equals 1. If x is equal to 1, then the first term vanishes. So we'll just have 2b, meaning b is 1/2. And then if x is minus 1, we'll have 1 equals -2a, and then the second term vanishes. So a is equal to -1/2. Okay, so therefore we can write our final answer. Remember, we're dealing with x squared over x squared minus 1 dx. We already knew that the answer should look like this. Okay, and what's left to be done is to plug in the values of a and b. A is -1/2, and b is positive 1/2. And there you go. We have the integral. All right. So lesson here, whenever degree of top is greater than or equal to the degree of the denominator, do long division first. Otherwise, our trick in the partial fraction decomposition won't work. Okay, let's try another one. Okay, again, interject if you have some questions in mind. Don't hesitate. Okay, so let's try problem number 3, which looks a bit intimidating because here the top is degree 4, bottom is degree 3, long division is required. So this would be a good exercise and a good recall of how to do long division. So I'll put the divisor here outside, and then I'll make a roof. Under that roof, I'll have the dividend. Do you guys still remember this? This is kind of nostalgic, right? Maybe the last time you did long division is in grade school, so this should bring up some memories, hopefully good ones. Now, how do we do this? Look at the first term first, divide it by the highest power here in the divisor. So we'll have x to the fourth divided by x cubed. That's going to be an x. And then what we do here is we multiply the quotient with the entire divisor. So we'll have x to the fourth minus 3x cubed. And then we will subtract the product from the previous level, right? So this guy minus this guy will give us minus 2x cubed plus 6x squared minus 18. And then we repeat the process. Take the first term here, divide it by the first term there. So you have minus 2x cubed divided by x cubed. That's minus 2. Then multiply what you got, negative 2 times the entire divisor. So we'll have negative 2x cubed plus 6x squared. And then do this minus this, okay? And we'll get 18. Oh, sorry, minus 18. All right, and then remember what we do. We'll have the quotient, x minus 2, plus the remainder, negative 18, over the divisor. Okay, and at this point, we can do partial fraction decomposition on the remaining fraction. Okay. But before doing that, maybe you can integrate the first two terms because they are just polynomials. So we'll have x squared over 2 minus 2x. I'll reserve the arbitrary constancy for later, or I'll defer it for later. So we'll have, or probably I can also write it as minus integral of 18 over x cubed minus 3x squared, but I can factor it as x squared times x minus 3. dx. Okay. Now we'll turn to that integral and do the partial fraction decomposition. Minus. Okay, so remember the first thing, we have an x squared here, so it will get one fraction in the decomposition, and then it would be ax plus b. Since the factor is quadratic, what goes on top would be linear, plus x minus 3 gets one fraction. It's linear, so its numerator must be 1 degree less. So I'll have a d there, dx. And I guess I can do the integration here easily. I can write the integral first as minus a over x plus b over x squared plus d over x minus 3. And each of these three terms inside the integral can easily be integrated. So we'll have x squared over 2 minus 2x minus a ln of the absolute value of x. Don't forget, I have a negative sign here, so that goes inside the three integrals there. So that's why you'll see a reversal of the signs later. Okay, then here I'll have a minus bx to the negative 1 all over negative 1. That's the integral of this, and then that negative sign goes there. So just making sure I'm tracking this all properly. Minus d ln of the absolute value of x minus 3 plus c. All right? Then let me just rewrite it a little bit. So x squared over 2 minus 2x minus a ln of the absolute value of x plus b over x minus d ln of the absolute value of x minus 3 plus c. And that's the final integral, right? Though what's missing here are the exact values of a, b, and d. That's what I want to solve next. And how do we get that? Well, on the side, I'll go back to the fraction that we decomposed. So we try decomposing this. And we said that our guess for the decomposition, oops, what happened? Oops. Okay, so now what our guess for the decomposition was this. I don't know, what are you more comfortable with? Doing the integration with those a, b, and d, or solve for a, b, and d first? I like integrating as long as I can, or whenever I can, but some students prefer solving for a, b, and d first before doing the integration. Either works fine, but for me, I just want to emphasize the calculus step, so that even if I am not able to solve for a, b, and d due to lack of time, I am able to illustrate that I knew how to integrate. Okay, that's the only reason why I'm doing it this way. Okay, and then let's do the cross multiplication. So I'll have 18 equals ax plus b times x minus 3 plus dx squared, and this should be true for all x. Now, being true for all x, I have the liberty to choose what x's I want. For instance, I want x to be equal to 0. If I do that, I'll have 18 equals negative 3b, right? So this will be 0. B will be there. This would be negative 3. That's how I got negative 3b. Okay. Plus d times 0. So there we go. We find a value of b, and it's equal to minus 6. Okay. Next, I can let x be equal to 3. And that's good because this factor becomes 0, leaving us only with the second term. So we'll have 18 equals 90. That means d is equal to 2. Okay. Now we ran out of good x's. I mean x's that will make one of the factors equal to 0. So let's give it an arbitrary value for x. Say x equals 1. I'll stick with the small integers. But again, you can pick any number, any fraction, any irrational number you want. That's fine. But pick the convenient ones. So here, I guess if I let x equals 1, I get 18 equals what? A plus b times negative 2 plus d. Okay, so I just replace all x's by 1. And then I'll plug in the values for b and d because I already knew them. So I'll have 18 equals a minus 6 times negative 2 plus 2. I subtract 2 from both sides, so I'll get 16 equals a minus 6 times negative 2. Divide both sides by negative 2, so I'll have minus 8 equals a minus 6. Add 6 to both sides, we'll get what? We'll get negative 2 equals a. Okay? So therefore, we can conclude that the integral of x to the fourth minus 5x cubed plus 6x squared minus 18 all over x cubed minus 3x squared dx is equal to exactly the same form that we got earlier. But now we already know what a, b, and d are. So a is negative 2. So this will become a positive 2 here. B is negative 6. So it would be a negative 6 here. And D is 2. So there would be a 2 here. Okay. And that's it. That's the end of the solution. All right. Does that make sense? Guys, why you put ax plus b in the numerator? You mean this. Okay. You mean this this step above? Okay, great. Now that's the rule. So whenever you have, whenever you're giving, you're decomposing a fraction into several partial fractions. Okay. So again, the first step is to factor the denominator, and the rule is for every non-repeated factor, you give it one partial fraction, and then the numerator will be 1 degree less than the original factor. So the original factor here is x squared. Okay, I give it a partial fraction, so it will go in the bottom. The rule is you always give it a generic polynomial of 1 degree less as the numerator. So this is degree 2. So the numerator, according to the rule, should be 1 degree less. So it should be degree 1, which is a linear function. It should be generic. So I'll have ax plus b on top. Okay. In contrast to the second factor is x minus 3. It's not repeated, so it gets a single partial fraction in the decomposition. So that's why we got an x minus 3 here at the bottom. And the rule says the numerator should always be 1 degree less. So x minus 3 is degree 1. A degree less than that will be degree 0, which is a constant. That's why I got that. Okay. That's basically the rule. The proof of that rule is basically just hinged on performing addition of fractions in reverse, which is purely algebraic. But I hope you will remember this rule. Okay. Okay, is that good? Okay. Other questions? None? Let's try another one. Let's see. Let's try the integral of x squared minus 29x plus 5 over x minus 4 squared times x squared plus 3 dx. Okay. Now let's check the degrees. The numerator is degree 2. Okay, that's the highest exponent in the numerator. In the denominator, x minus 4 quantity squared will have an x squared in it. Okay, so the first factor is degree 2. The second factor is degree 2. So in total, the denominator is degree 4. So definitely the degree of the denominator is larger than the degree of the numerator. So we can do the partial fraction decomposition. Okay. Now, okay, I can do the decomposition. Maybe I'll focus on the decomposition first, because I'm not sure if the integral can easily be evaluated with the constants a, b, d, and e. So, but anyway, let's do the decomposition first. Okay. Now, let's look at the factors. The denominator is already factored, so let's analyze them. So here we have x minus 4 quantity squared. It is quadratic, but you should think of it as a repeated linear factor. It's just x minus 4 being twice a factor of the denominator. Okay, so whenever you have repeated factors like this, the number of repetitions will also dictate how many partial fractions will correspond to that factor. So here x minus 4, x minus 4 is repeated twice. So that means it will have 2 partial fractions here. Okay, 2 partial fractions dedicated to x minus 4. But their denominators will be increasing powers. Okay, so this would be the partial fractions corresponding to x minus 4 repeated twice. And then the numerators here will be 1 degree less than the original factor. Remember, the original factor is x minus 4. It's just repeated twice, so it's linear. So the numerators for both of this partial fractions will be constants, right? They will be generic constants, say a and b. Okay. Plus the second factor is x squared plus 3. X squared plus 3 is irreducible, meaning it cannot be factored anymore. So let's have x squared plus 3 there. But look at x squared plus 3. X squared plus 3 is quadratic. So that means the numerator should be 1 degree less. So it should be a generic linear function. Okay? Because always it should be 1 degree less. All right. Now let's do the cross multiplication. So here we'll have x squared minus 29x plus 5 equals. I'll have a times x minus 4 times x squared plus 3, okay, plus b times x squared plus 3 plus dx plus e times x minus 4 squared. And this should be true for all x's. Okay. So here I just used the concept of least common denominators that you learned from algebra, right? Because you can imagine this to be both sides being multiplied by the denominator, right? So a already has an x minus 4, so it only lacks an x minus 4 and an x squared plus 3, because I'm comparing it with this guy. If you look at the second term, it already has an x minus 4 squared, so it only lacks x squared plus 3. That's why that's the only multiplier. And then the third fraction already has an x squared plus 3. All that's missing is an x minus 4 quantity squared, and there you go. Okay, and this should be true for all x's, okay? Now, let's see if we have a convenient choice for x. Well, I can choose x to be equal to 4. And then if x is 4, then we'll have on the left 16 minus 116 plus 5 equals plug in 4. This will be 0, making the entire thing 0. The second term will be 4. That's going to be 16 plus 3, so that's going to be 19b. And then third term, this will become 0, so that entire thing will vanish. So we'll have this. And let's simplify the left. It's going to be negative 95 equals 19b, meaning b is negative 95 over 19, which is negative 5. Okay, that's the first value. B equals negative 5. And then if you look at the left-hand side, there doesn't seem to be any other convenient choice for x that will make sum of the terms equal to 0. So you can start giving arbitrary values for x. That's fine. But let me show you another method. Okay. So if you run out of good values for x, then another way to do it is to carry out all the multiplications here. So multiply this thing out, multiply this guys out, multiply this, and then add them up together. So basically what I'm trying to say here is you expand the right-hand side. So if you expand the right-hand side, the next thing is to collect all the coefficients of x cubed, all the coefficients of x squared, all the coefficients of x, and all the constants. So if you do that, so here you expand or carry out the multiplication on the left-hand side, and then collect like terms. When I say like terms, these are the terms with the same power of x beside them, okay? And if you do that, you'll get this. You'll get x squared minus 29x plus 5 equals, hold on, I did it earlier because I expected the solution to be long. You'll get a plus d x cubed plus negative 4a plus b minus 8d plus e times x squared plus 3a plus 16d minus 8e times x. And then the constants will just be plus negative 12a plus 3b plus 16e. Okay, so I skip a lot of algebraic steps here, but again, all you need to do is to expand this out, meaning carry out all multiplications. So you will have a very long polynomial. And the next step is to collect all like terms, all right? So for instance, we need to collect all those with an x cubed. So you see here, you'll have x times x squared times a, we get ax cubed. That's why I got an a there. And then you have a dx times, when you expand this, you get x squared minus 8x plus 16. You multiply it with dx, you will get a dx cubed. And I hope you see that how long and painful that process could be, okay? But if you're patient enough, you'll get this. I guess it might be easier to just give some values for x, 0, 1, 2, -1, -2, and then come up with a system of equation. And either way, you'll get the same answer. I just picked this step just to illustrate both sides, okay? Now, what's the advantage of this technique? Well, this technique will tell us we can compare coefficients, okay? So note here, what's the coefficient of x cubed on the left side? There's no x cubed appearing here, so we can imagine that it has coefficient 0, okay? Then what's the coefficient of x cubed on the right side? Well, on the right side, the coefficient of x cubed is a plus d. So that means for these two polynomials to be equal to each other, then a plus d must be equal to 0, so that they will have the same coefficient for x cubed. So that's the principle, okay? Now for x squared, the coefficient of x squared on the left is 1, right? So you have a 1 here. But the coefficient of x squared on the left-hand side is this long expression, minus 4a plus b minus 8d plus e. Okay? And then the coefficient for x is on the left, minus 29. It must be equal to the coefficient of x on the right side, which is 3a plus 16d minus 8e. And then lastly, for the constants, okay, the right side, on the left, the constant is 5. On the left, the constant is minus 12a plus 3b plus 16e. And we have ourselves now a linear system of linear equations with 4 unknowns, a, b, d, and e. Okay. But we can take advantage of the fact that we already know that b is equal to minus 5. So let's rewrite this as a system. The first equation, I'll have a plus d equals 0. Let's call this equation 1. Okay. And then for x squared, we'll have what? Negative 4a. I know that b is negative 5. Minus 8d plus e equals 1. Maybe I can, okay. Maybe I can transfer the minus 5 into the right side, so it will be a plus 5, so this guy will be 6. Okay. And then the third equation will become 3a plus 16d minus 8e equals negative 29. Is that good? I think so. Okay. And then the last equation would be minus 12a. I know that b is negative 5, so I'll have a minus 15 here, plus 16e is equal to 5. And then I can put this minus 15 as a plus 15 on the right side. So I'll get a 20 here. And then put that here. Okay, let's call them equations 1, 2, 3, and 4, respectively. Okay. Now let's try to finish it quickly. Now look at equations 2 and 3. Okay. So we have, let me just copy them here. Because they both have the same variables, so that's why I want to use them. And I'm targeting to use this equation or the resulting equation with equation 4. Equation 4, or actually, should I do equation 4? Yeah, I want to do it with equation 4. So I want to eliminate the variable d. Okay, how do I eliminate the variable d? I can multiply this by 2, right? So that the coefficient of d would be -16, and then I can add the two equations. So basically, this is solving equations by elimination, right? So I multiply the first by 2, so I have -8a minus 16d plus 2e equals 12, right? So basically what I did here is to multiply by 2. And then I'll just copy the second equation, 3a plus 16d minus 8e equals -29. I wanted to do that so that I can add them together. So we'll get -5a minus 6e is equal to -17. And then let's call this equation 5. I hope I did the calculations right. Anybody doing the calculations with me? You guys still there, or are you already packing for the packing for the spring break? So now I can use equations 5 and 4. Okay, let me do this on the next page. Okay, so equation 5 is this. Equation 4 is this. Yeah, I'm just doing it now quickly because of lack of time, but yeah, just try to absorb the process and hopefully try doing it on your own later, okay? Now, what I can do here is to multiply the top. I want to eliminate the variable, I want to eliminate e. So if I want to eliminate e, I'll multiply the top by 8 and multiply the bottom by 3. So that the coefficients of e will be -48 and +48 respectively. That's my choice because I don't want to do with large to work with large numbers. But you're going to also multiply this by -12 and this by 5 so that you can cancel a. That's also fine. So it's just my personal preference because that's what I did before. I actually computed it earlier, so that's why I can do it fast. Because I did it earlier. So what I'll get is -40a minus 48e equals -136, and minus 36a plus 48e equals 60. Then I add these two together to get -76a equals -76. A is just equal to 1. Okay, so we have two numbers, two values down. So let's see what else can we find. Okay, I already know B and A. So B and A. I guess I can solve for E. Yeah, I can use this equation to solve for E. Now from 5, I can use A equals 1, so I'll have -5 minus 6E equals -17. Minus 6E is equal to -12. and then E is equal to 6. And we're down to the last one. What's the last remaining variable unknown? I think it's D. So pick any equation that has a D in it. Let's try equation 1. Oh, that's easy. So from equation 1, we knew that A plus D is equal to 0. So, but we already know what A is. A is 1. So D is equal to -1. Now we all knew the constants, so we can plug them into this. Okay. We already know what A, B, D, and E are. Plug them in, and then you can integrate term by term. And hope that that integral will be easy to compute, right? So sorry, I went over time today, as often. But okay, what I'll do now is to complete the solution before uploading the annotated worksheet. Take a look at it. If you have nothing much to do during the spring break, then try to answer as many problems, and let me know on Monday, week after next, if you have some other questions. All right. So everybody enjoy your spring break, but stay safe, and let's see each other again week after next. All right. Bye, everybody. Yeah, that's a lot. That was a long one.